All right, everybody, give it up for Q.
Hello, everyone. So this presentation is about the USB protocols. It started out as some research for the CTF, and I was amazed that the protocols even worked in the first place, so I started digging deeper. Yeah, not necessarily something you want to dig deeper into. It's very wordy, but here we go. Who am I? I'm Q. Well, I'm Quintin. Most of you know me as Q. I'm a fourth year here, competition architect in charge of the CTF and IRSec. I am not very good at memes. As you'll notice in this presentation, there are none. And I'm at Data Frogman for most services. So, what is USB, or the Universal Serial Bus? So it is a standardized connector and process used by, or implemented and maintained by the USB Implementers Forum. There's a lot of companies involved in it, and they really like their PR speak, and as a result, the documentation is very wordy. So the USB protocol uses a star hub, or tiered star hub approach, allowing for chaining and the use of 127 devices out of one hub. So the host device is known as the root hub. Anything going out goes away from it. Anything going in goes towards it. You can connect hubs and devices branching out from there. However, since it is a master-slave protocol, the host must ping or request data from the devices and pull them to get any information. You can't go from a device towards the host, except for some very, very specific exceptions. It has gone through many forms and iterations through the years, including some controversial ones with USB 3, 3.1, 3.2, and the super speed versions of them. They're interesting. So some forms and formats. The protocol was originally created in 1996 with the USB 1.0. Very simple. It's USB that you know and love, except it was only 4-pin versus some of the newer formats. It was updated in 2001 to 2.0. In 2011, it was updated again to 3.0. 2014, it hit 3.1. 2017, 3.2. And in 2019, it hit USB 4. Most people call the versions 3.1 and 3.2 just 3.0 revised because of how many actual revisions it went through in that short period of time. And the standard format has only 3 types, A, B, and C. A is what most people are used to. B is if you have a printer that's wired, the weird square plug. And C is the solution to USB superposition, where you always plug it in wrong unless you look at it. Type C is the only standard format available for full USB 4 speeds, which is 40 gigabits per second, slightly less if you implement FireWire over it. Mini has Mini A, B, and Mini AB. They're interesting. Micro has Micro A, Micro B Super Speed, which is A and B glued together, and then Micro AB, which is A with B inside of it. Most of those have fallen out of use, except for some older Samsung phones and older Android devices, as more devices are moving to the 4.0 standard and supporting USB-C. The mini and micro formats were fully deprecated in 3.2, and as a result, you don't really see many new devices using them. So, packets. We're going back to routing and switching, everyone. Well, OK. So when you start doing research into USB, you'll notice that a lot of people start arguing that the packets over the USB protocol are not real and it's just an abstraction. Unfortunately, that's not true. It does utilize packets, but it's not part of the network stack. It just sort of does its own thing. So the packet format follows, all of them have the same format. Sync section, PID, and then data. Sync is a sequence of Ks and Js. A lot of them. Don't know why. It's just KJ, 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 and then eventually KK. I don't know. It's just what they decided on. Really arbitrary, but every single packet must have that.
SMS came out at the same time.
Okay. There are four main categories: handshake, token, data, and special. Handshake started out as ACK and NAC only, then USB 2 added NIET install. Token supports out, in, start of frame, and setup, and then with 2.0 added split and ping. Data originally only had 0 and 1 and added 2 and M data with USB 2.0 and 3.0 respectively, and then special typically is only used in 2.0 and higher, though it is quite special. So I'll be saying PIDs a lot. If you want to check out the slides later for reference, PIDs are in this nice handy-dandy table that someone formatted after reading the 600-plus page documentation. Once again, it seems kind of arbitrary. It's just the binary format of the designated numbers for them. Now, the PID is 1 byte long in all of the packets, despite only being 4 bits. It duplicates the PID in case of any data loss and to fill out and pad the packet. So, handshake packets. These are very simple. It's the sync, of course, then a PID byte with the same packet type twice, and that's it. Doesn't need data. With USB 2.0, we got the NIET and error packets, though error is also considered a special packet. It still is technically a handshake packet. ACK is same with networking. I receive data, and I'm acknowledging it. NAC, your data transmission was unsuccessful, retry. Stall, you can't send me data right now. Don't. Just don't. I'm done. Unplug me, plug me back in, or restart your bus. I'm done with data. Bye. NIET is a very interesting usage. It's used to designate when a split transaction is not complete. We'll cover split transactions later. It's also used to indicate when a buffer is full. So if you're transferring large amounts of data and you fill up the buffer, the host device will start sending back NIETs or vice versa, and that'll indicate the buffer's full and stop throwing data packets at me until I clear my buffer. This allows whatever device is sending the data to send ping packets, which are much smaller, to maintain the connection to check when the buffer is clear. It'll continue to get NIETs back until the buffer is clear. Error is a notification that the split transaction has failed. We'll cover split transactions later on, but this is also considered a special packet. Down in the bottom, I have a indicator or table of what the packets look like: sync signal, and then the PID, and then end of packet. That's all handshake packets are. Token packets. Now, these are interesting. They pretty much set up and are used in handshakes and other specific sections. They're the sync header, a single PID byte indicating what type it is, and then 2 payload bytes. In and out are the most commonly used ones. For their data packet in the payload, they have 7-bit device address, which, yes, just like in routing and switching, we have more physical addresses. But these aren't MAC addresses. They're different. These are just an indicator of what number device you are in the tiered star hub. I don't know. Then it has a 4-bit function number if you're using a multifunction device, and then 5 bits for the in-out command. In will accept a NAC stall or data-X response. It's saying, hey, send me data. Out is followed by a data-X, so a data packet response, pretty much saying, hey, here's some data, and then sends the data packet. And it expects an ACK, NAC, NIET, or stall. ACK saying, I received it. NAC saying, hey, I don't want it. NIET saying, hey, I'm full, stop it. Or stall saying, hey, stop. Setup. This will be the most commonly seen packet with USB. When you plug in a USB device, it will, first time it's pulled, send a setup packet. It has a 7-bit device address, and then a 4-bit function number, and then a 5-bit setup command. It is then followed by an 8-byte, that's a typo, a 8-byte data 0 packet. Start of frame, these are used to keep tabs and keep a connection open between a device. It contains a 11-bit frame number and a 5-bit checksum. Every single millisecond or 125 microseconds for high-speed devices, the host will send a start of frame packet incrementing the frame number each time. When it runs out of space, it just starts all over again. Ping, so these packets have a 7-bit address, a 4-bit function number if it's multifunction, as usual, if it's multifunction, and a 5-bit command. These are exclusively used to check if a device is ready to receive data. You normally see it after a NAC or a NIET, but it shows up randomly sometimes. And it expects to receive an ACK, NAC, or stall, pretty much saying, hey, are you able to receive data yet, please? And then you'll get a yes, no, or a just unplug me, I'm dead response. And then a start or complete split token packet. These are used for split communications. These packets have a 7-bit address, a 1-bit flag to say if it's a split or a complete, and then 0 to 8,192 bytes of data, a 7-bit port number, a 1-bit speed flag, and a 1-bit end flag or reserved flag, and then 2-bit end type, and a 5-bit checksum. These are used, so split tokens or split packets are used to transfer data over ports that are not matching in speed. So if you have somewhere along your chain, you've got a high speed, then a low speed, then back to a high speed. To bypass that buffer, it uses a split packet so that it doesn't get stopped with trying to send a high-speed packet through a low-speed zone. It'll break it up into however many necessary packets and then just drop each of those in slowly till it gets through back to a high-speed zone. Data packets, now these are the simplest. Well, actually handshake packets, but these ones are pretty simple. You've got your sync, your PID, 0 to 1,024 bytes of data, and a 2-bit CRC. Now, or 2-byte CRC. Now, they don't always have a CRC when it comes to human interface devices, specifically those using the URB protocol, which we'll cover later on. Data packets must be preceded by an address token and then followed by a response token. Much like with TCP, if it does not receive a response, it'll assume that someone lost it in the way and then resent. The devices must store the previous packet to check if the response was missed instead of missing the next data packet. So you have to use alternating data packet types. That's why we have data 0 and data 1. So if I send a data 0 and I don't receive a response, I then send it again. If for some reason the receiving device receives the data, then sends the response, but the response is missed somewhere in between, and then receives the next data packet, it'll see, oh wait, this is a data 0 and I just received a data 0, or this is a data 1 and I just received a data 1, and then trash the packet and send another response. There are also data 2, which are used for high-speed transactions, and M data, which are used for even higher speed transactions. The protocol isn't very creative with names. It just sort of keeps incrementing the numbers. So special packets. The pre-packet is very useful. It has a 1-byte PID, and it tells the hub to enable output. Then low-speed packets occur. Then the hub disables its low-speed output. So hubs are hubs. They just repeat everything you send to them without care for anything connected. There's a possibility that a high-speed hub can have a low-speed device connected to it. If you try to send high-speed packets to a low-speed device, it'll only get the first section and act as if it was a normal low-speed packet. So you end up getting things garbled and messed up in the middle. So to solve this, you disable the low-speed hubs or the low-speed devices until they receive a pre. Then they'll receive a re-enable for a short period of time, accept the data, and then shut off again. Then we have error packets. They are a special error packet or special handshake packet used to say, hey, your split connection, it didn't work. Pretty much all it's used for. So one of the really fun ways that USBs are used are human interface devices, which, yes, rubber duckies do count, though not the kind you have in your bathtub or mounted on your Wi-Fi access point if you live in my apartment. So human interface devices are anything you use to interact with the computer. Mouse, keyboard, driving simulator, uninterruptible power supply. There's a whole lot of things that count as human interface devices, even though a lot of them really shouldn't. So your standard human interface device is your mouse and keyboard. They're CPU polled, and they typically cannot send operating system interrupts. So they have to wait for the operating system or the CPU to say, hey, give me the data that you have, and then they just hand over the data that they're waiting to or they have queued up. So if you hit A on your keyboard, it just sits and waits, and then the CPU fetches that data and sends it back. Now, there are keyboards that are set up with the USB boot keyboard profile. They send interrupts with every single poll, so the CPU has to stop, accept the data, and interpret it, instead of most keyboards, which when the CPU polls, it can just wait and sit on the data without interpreting it until a later time, depending on what it's currently doing. So if it's under a high load, it'll just ignore until it gets a chance to interpret it. So these send a specialized DataX packet, now the contents of which depend on the human interface device and the keyboard protocol, and they use the URB protocol, or the USB request block protocol, to communicate from driver to OS. This protocol is modified forms of data packets without the checksum. So the data transferred over it is not guaranteed to be correct. This is really fun to think about when you realize that this is the only way you interact with most modern computers. So if you're typing on your keyboard, there is a possibility that all these packets get mangled in the process, and you spamming the W key or F5, the computer doesn't realize you're actually doing that and thinks you're doing something else. I couldn't really find any reasoning why in the specs, other than just because. Now, this particular protocol is vulnerable to bad USB attacks. Bad USB attacks are popularized by the USB rubber ducky. They are when you plug in a computer into the USB port into another computer, and it declares that, hey, I'm a keyboard, or I'm a different human interface device. And because USBs are trusted implicitly, the target computer is like, OK, you're a keyboard. Tell me what you want to send me. And you can type in or send malicious data. A mitigation for this is to disable all USB ports on the device and use only PS2 ports for human interface devices. PS2 ports are not trusted implicitly in the same way, and they do also have the fun fact of they are not hot swappable. So you plug it in, you boot up your computer, and if you unplug it, you have a good chance of crashing your computer. So be careful on unplugging your mouse and keyboard then. Then we get to other human interface devices. So if the designer of a device decides to make it compliant with the HID standard, which is over 100 pages long, it is a human interface device and can just be plug and played on pretty much any computer. There are generic drivers that will communicate and interpret packets from human interface devices properly, though some more specialized ones do need drivers installed, such as UPSs or simulators. You will see these really frequently with TTY machines. TTY machines are set up to be human interface devices, both accepting audio, keyboard input, and output to a screen. So some resources. The USB implementation forum at usb.org does host all of their docs. I actually wouldn't recommend you go to the source for these. The docs are typically 650 plus pages for each implementation, and they're written by marketing. They suck. They are not fun to read through, and they're even worse to try to interpret for the actual technical specifications. There's a couple places that I'd recommend to head to for the older specifications. Beyond Logic and USB Made Simple cover USB 2.0 and earlier, so a little outdated. However, it is very good for learning the basics because the more recent stuff builds upon the older implementations. For human interface devices, the OS Dev and Microsoft Docs cover the Linux and Windows implementations of human interface devices and are very easy to read and go over. And so does kernel.org for Linux devices. If you're interested, come talk to me. It's a very cool topic. It just takes a lot of reading. And there are quite a few sites online that will give you a little cheat sheet of, hey, if you want to look at the actual protocol, jump to page 200 and whatever in this specific document, and then skip to 300 whatever on this document. And it's very useful, so you don't have to deal with marketing the entire time. Any questions?
Thank you.
Such a boring topic.
All right, guys, so that's all that we're going to have on the stream. So for everybody on stream, thanks for coming out, and we will see you guys next week. For everybody in here, Becca's up next talking about some stalkerware. So are you on your own laptop or on this one? All right, this one works. Bye, stream. Bye, stream.